This will be, today and tomorrow, this will be the most conceptually difficult stuff that we do in the entire class. Okay. There's a part of me, anybody had biochemistry? Just Riley. Outside of Riley and what they do in biochemistry, which all we're doing, this is just biochemistry, right? You haven't had biochemistry. This may be as difficult a thing as you guys will encounter conceptually in the entirety of your undergraduate experience, right? When I teach it to our graduate students, this is the most difficult thing that we have for all of them. It's difficult, okay? I'm going to try my best to get you guys to see the big picture while we learn the details, because we're not just going to memorize pathways. We're not just going to memorize the steps in glycolysis. We're not just going to memorize the steps in the Krebs cycle. In some ways, in fact, I've decided you guys aren't going to do that. We're going to talk about what goes in and what comes out. And we're going to talk about some key enzymes and control steps, because I want you all to try to focus on how this fits together. Because if you get that, it will make sense to you why, if we go out and we start jogging, we feel the way that we do. And then after about 10 minutes of jogging, you feel a little bit better. It's all explained by metabolism, right? It will all explain why you go and have pasta before you have a marathon, right? There will be all of these things that will hopefully make some level of sense. And we're going to get into these particular pathways, okay? So metabolism is, at its most basic, a way of creating energy, making ATP from some sort of molecule that we will call a substrate. Okay. So in this picture, protein can be a substrate. As we break them down, we make ATP by breaking them down. Okay. The same thing with carbohydrates. Carbohydrate is a substrate. Fat can be a substrate. Okay. So when I talk about what is the effect of different substrates on the pathway and different substrates or different exercise intensities on the substrate that we use, this is what I'm predominantly going to talk about. Okay? And we're mostly going to focus on carbohydrate metabolism and lipid metabolism, because to be real with you guys, if you're doing protein metabolism, you need to go eat something, right? You're probably in a negative caloric balance, and we probably need to eat something. Okay, we only do this in a lot of ways as kind of a last resort. Okay. All right. I want you to repeat this mantra, okay, as we go along here. First mantra of metabolism. Okay, write this down. This may be the most important conceptual thing that we cover, that's why we're doing it first. Okay. Every energy pathway is active all the time. Every pathway is going all the time. Mantra 2. Every energy substrate is being broken down all the time. All pathways, all the time, all substrates, all the time. Okay. Told you guys we don't do much with protein. You're always breaking a tiny fraction down. If it's predominant, no way. Okay. I just used the word predominant. Who knows what the word predominant is? Hello? Main, okay? Dominant, main, majority, okay? Because all the pathways are on all the time, all the substrates are used all the time. I'm going to talk about this as which pathway is the predominant pathway, right? Which pathway is providing the most energy at a given moment in time for a given activity. Similarly, we will talk about which substrate is the predominant substrate that's being broken. Okay. All right. Also, why should we care about metabolism? Well, many of you did a very nice job getting all the CrossFit stuff like that. Very, very impressive. Does well with that as any class, any of my graduate classes as well. So I applaud you. Right? In order to run the cross-bridge cycle and continually generate force, what do I need? That might be related to metabolism. ATP. A lot of textbooks put this first. I put it after muscle contractions and all of that stuff because we need the ATP from metabolism to support the contractions we just learned about. Okay? To support the force generation that we just learned. And hopefully that will make sense to you then when I'm saying if we walk versus running, I go from Destiny goes from sitting to walking, force production goes up. So she needs more ATP. She goes from walking to jogging, force production goes up. So she needs more ATP. She goes from jogging to sprinting, production goes up. Okay. Most of the ATP that we make in metabolism goes to the myosin ATPase. It goes to run the sodium potassium pumps, and it goes to the calcium ATPase. Right? 80% of all the energy that's ever used in your body is for that. Heart gets some. Well, the heart has myosin ATPases too. You guys know that. The heart contracts some muscle like everything else. The brain uses some. We get no energy, we get no movement, we get no bodily function. Okay? And that's why people put metabolism first. You don't have the metabolism, you don't have the ATP, you can't do the muscle contraction. I see that. But I think conceptually the way I want to teach it is better this other. Additional significance. Okay? We're going to talk about metabolism today and tomorrow. Friday, we're going to talk about how we control blood glucose. Talk about carbohydrate. The hormone response when you exercise is done directly to help us with metabolism. The increase in heart rate, the increase in stroke volume, the increase in cardiac output and blood pressure and where blood goes and breathing rate and breathing depth. Pretty much outside of the stuff in the muscle, every physiological response to a bout of exercise is directly related to ATP turnover and metabolism. Cardiovascular system functions to bring us oxygen and substrate so we can run metabolism. The pulmonary system brings in oxygen, gets rid of CO2 to support metabolism. Okay? So this is where we're going to get a lot of physiological responses are going to come from here. Many training adaptations are proportional to the energy expended during a bout of exercise, especially chronic aerobic training. Okay. Performance in athletic events is often limited by the availability, the significant or an adequate amount of ATP to continue exercising, especially in sprints and especially in very long distance. Okay. I asked Anna to stand up and sprint as fast as you could. How far do you think you make it, Anna, before you slowed down? Think you could run 100 meters at exactly the same speed? Think you're going to slow down a little bit by the end? Okay. Why does she slow down? She runs out of ATP. She cannot get enough ATP to continue contracting her muscles at that much force. When you run a very long distance, to run faster or to run farther, you need more energy because you got to generate more force. So this is all going to be part of it. Very end of stuff tomorrow, we're going to talk about this idea, this concept called fatigue. Fatigue is a failure to produce the expected force production, right? I used to be able to do this a second ago. Now I can't. Cannot do another rep when I'm lifting weights. I cannot run at this pace again. I cannot pull the oars at that force one more time. Okay? That's fatigue. A lot of fatigue is based upon lack of ATP or things that come from metabolism that actually inhibit our ability to do. Okay? That's our context. Okay. All the pathways all the time, all the substrates all the time. And we're supporting force production. That's where we're going to start from. Okay. Okay. So let's talk about energy just a little bit. Okay. We can define energy as an ability to perform work. Okay. It emerges only when change takes place. And this is going to get into sort of the concepts of bioenergetics and the first law of thermodynamics. Anybody had physics or something? It was chemistry, did the first law of thermodynamics, right? Energy cannot be created or destroyed, but it's transformed from one form to another. That's what we're doing with metabolism. I'm taking energy from that glucose that you just ate, or from that cheeseburger that had fat and carbs and protein in it that you just ate. And I'm going to break it down and release the energy from it. And then I'm going to use that energy to do work in my muscles. And then I'm going to use a metabolic pathway to then resynthesize some of that. We'll talk about that. This becomes a really, really important concept. Okay? The idea that with metabolism, we take substrate and we strip stuff off of it, break it down, make ATP, and we use up the ATP, and then we just recycle the whole shoot. That's what's happening. Now, I mentioned total energy is potential energy plus kinetic energy. Potential energy is associated with a substance's structure or position. Food has potential energy in it. Kinetic energy, they say it's energy in motion, right? Kinetics, kinesiology, it's motion, movement, those kinds of things. Okay? Don't worry about exergonic and endergonic and biosynthesis and these kinds of things. This is some kind of high-level chemistry and biochemistry stuff. Just want to let you see these things in case you get them. But I do want you to know potential and kinetic energy. Okay. So when we think about doing work or making energy, right, within the human body, okay, we are going to have chemical energy, right? Chemical work, which is the biosynthesis of cellular molecules. This is making glycogen, making fat. We're putting things together, okay? That is what's going on there. Mechanical work is a muscle contraction. That's what's going there. Contracting our muscles. And then we may use stuff to transport stuff along cells. We may have to actively transport them, which is going to also cause work and cost us some energy. The sodium-potassium pump, where we're pumping ions against their gradient, that is a transport kind of work. Okay? We're really going to focus on, we already focused on mechanical work. We're going to focus on sort of the breakdown, right, of molecules to help us support that. Okay. Our energy substrate or our energy molecule is ATP. Hope this isn't okay. So there are roughly 7 to 10 kcals per mole of ATP. That kcals is whatever's written on the back of the label of your food packages or whatever it is that you're drinking. Okay? The amount of calories in a substance is just one way of telling us about how much ATP can we derive from the molecules contained in that food or drink. Okay? So when you see a calorie, what it really is a kcal. Okay? Important point. You actually have a very small amount of ATP in the cells in your body. Very small amount. Okay? That's because those cells are taken, a lot of the space is taken up by all of the other things that those cells need to function. There's not that much room to have a lot of ATP in there. So because of this, what we're going to do is you start a muscle contraction, let's just say, and you use some ATP, you will very quickly lower the amount of ATP that is in those intracellular stores. Okay. Now we have to do metabolism in order to make that ATP come back. And that's what we're doing, guys. You have ATP, you strip a phosphate off, you get ADP, and then we're going to use a metabolic pathway to put a phosphate back on. It just goes around and around and around and over again. Okay? That's what we're getting there. We're going to use several pathways, we use several substrates, which we will talk about. Okay? Pathway and substrate that predominates is going to vary wildly based upon the actual muscular domain that you place right on those pathways. So the mode of exercise matters. Intensity of the exercise really matters. Moderate intensity, heavy intensity, presence or lack of oxygen. We're here at sea level. We pretty much have oxygen all the time. Your state of training and your diet. We're not going to get into all of these kinds of things in excruciating detail, but they're all going to matter. Okay. As an example of diet, if all I do is feed you carbs, you're mostly going to use carbohydrate. All I do is feed you fat, then you're going to break out and mostly use fat. Okay. That's the importance of sort of what the diet is. We'll get at the state of training a little bit later. Okay. Are you guys with me so far? This seems reasonable so far. Some of you, has it been years since you talked about this, dude? Y'all cover this in like personal, we don't do it in 3813. We don't do it in health and fitness. Y'all cover this in like endurance training or personal training or anything. Y'all do the metabolic pathways at all. So for some of y'all, it may be since like chemistry or biology when you're a freshman. Kayla? Little in sport nutrition. Okay, so Sarah did a little. Okay. All right. I mentioned what these things are. We'll come back and talk about those. Now some word soup. It's important. Here are many words that look and sound very similar, but all mean very distinct things. Okay? Glycolysis is the idea where we break down a glucose molecule into ATP and lactic acid. We're going to modify that a little bit, but that's the general idea. That's what glycolysis means. The lysis. We're breaking down glucose into this. Okay? Then we have glycogenesis. Genesis meaning to put together. Glycogenesis is when we make glycogen from glucose. Okay. Then there is glycogenolysis. Okay? Which is the opposite of glycogenesis. It's taking glycogen, breaking it down into glucose. We'll talk about this in a few minutes, but this is a very, very key process that we do in our muscles and that your liver does to maintain blood glucose levels. A lot of it is driven by an enzyme called phosphorylase. Okay? Driven by an enzyme called phosphorylase. Lastly, I'm just going to mention it here, and we're not going to talk about it further, is a process called gluconeogenesis. Gluconeogenesis is when we make glucose from non-carbohydrate substrates in the liver. Okay? Especially we make it from amino acids from like protein. Sometimes you can make it from fat. Non-glucose substrates. A little bit of this is happening all the time. All of these. Okay? But we'll get at the idea that when you start to exercise and do muscle contractions, glycogenolysis or glycogen breakdowns dominate. That's going to happen a lot. We're going to get a lot of glycolysis. It's also going to happen. Okay. don't have to know these numbers, but I like to show the numbers because I think it's a really kind of stark and staggering thing to see. If we look at how much carbohydrate you have stored in your body, in glycogen in your liver, glycogen in your muscles, and then glucose contained primarily in your blood, okay? You probably have, an average person probably has about 1,500 calories of carbohydrate stored, okay? For many of y'all, that's not enough to sit on the couch all day. That's higher than, that's less than what your resting metabolic rate would be. And most of you eat every day. That's what we are. If we look at fat levels, we have mostly subcutaneous fat. There's a little bit of fat in between your muscle fat, intramuscular. But you have about 72,000 kcals. Okay? About 72,000. So an average person has a tremendous store of fat that it can mobilize and use. You guys will see how that process very often gets driven when we talk about the hormones. Right? So if you had to look at these two, which one do you think it would be preferable for your body to use? Push comes to shove. Should I use carbs? Should I use fat? Okay. Why carbs, Avery?
Oh, I think about my body does. It uses carbs.
Okay. Yes, that's right. It does use them because they are a little bit quicker. But should it? If you had a bank account that had $72,000 in it, or a bank account that had $1,500 in it, you needed to go to the grocery store and buy something today, from which account would you feel better about charging whatever it is that you bought at Walmart?
Which one's like the savings? And which one's like
That's
the check?
Okay.
Technically, it's fat.
Yeah, I feel like that's like more of like a savings account.
Yeah.
And you use all the checking, you're like, oh shit.
Maybe is that kind of like correlated?
That is in some ways actually what ends up happening most of the time. My metaphor was just really bad. Okay. And I suppose in some ways the correct answer is it doesn't matter where the money comes, it's still the same amount of money and you still have the same amount, regardless of where it comes from. Right. Okay. Scrap all of that. All of that makes no sense. Okay. We'll talk about this a little bit later on, so you have to write it down. What tends to happen during exercise is you can get ATP from carbohydrate faster. It's a faster process because it has fewer steps. Okay. But the amount that you have is somewhat limited in comparison to like. So you're going to see that as duration of exercise changes, as some other things happen, we're going to try to shift ourselves whenever possible to use as much fat as we can for energy and use as few carbohydrates as we can. Sometimes that's not possible based upon whatever exercise it is that you're doing. But we'll kind of talk about the push-pull of those things. And I'll show you guys the pathway where we break down carbohydrates and then the pathway by which we have to break down fat. And you'll be like, oh yeah, I get it. That's why this takes forever. So we'll come to that. Okay. One of the possible advantages of breaking down fat is that you actually get, it's more energy dense. You get 9 kcals, right, for breaking down 1 gram of a free fatty acid, and you get 4 from breaking down 1 molecule of glucose or 1 molecule of some protein, or 1 gram of some protein. Okay. And again, because there tends to be sort of, there's the same number of carbs, but there's more hydrogens and things on here. So the way that we have to strip stuff off through the Krebs cycle, we actually end up generating a little bit more here. Okay. So if you can use fat, you actually get more energy or more ATP out of it per gram that is possible to use. Okay. None of the stuff you guys have all been doing. What are the pathways? Okay. So we're gonna go through the pathways. And there's gonna be some parts of this that I want you guys to memorize. Just gonna have to memorize it. There's no way around. Okay. There is pathways that we're gonna call immediate energy pathways. They're oftentimes called phosphagen pathways. Okay. These are going to be, as you all will see, these are immediate because they're basically one-step reaction. Okay, one-step reaction. There is molecule of ATP, I'm going to pull a phosphate off. There's a molecule of creatine phosphate, I'm going to pull a phosphate off. I may run the myokinase reaction where I take two ADP molecules and I smush them together and I get an ATP and an AMP. Okay, so these are going to be limited in their amount, very limited, and we're going to get energy from them very fast. Okay? All of these reactions, and this is an important thing, all of these reactions are going to occur in the cytoplasm of muscle fiber or whatever cell that we're going to. Okay? You have floating around inside of a muscle cell in a fiber, there's ATP that's floating. You have creatine kinase or creatine phosphate, floating around inside a muscle. In the cytoplasm. These are going to be reactions that are referred to as anaerobic. Why are they anaerobic? What makes something anaerobic? It doesn't require no oxygen for this. This is going to make sense for this. It may be tricky for you when we get into talking about glycolysis, depending upon how you guys have been taught glycolysis. Okay? Okay. Those are the immediate pathways. Very fast, severely limited amount of energy. Then we have what we call a non-oxidative pathway, which we're going to call the glycolytic pathway. Okay? Glycolytic pathway. This also occurs in cytoplasm, and it uses no oxygen. No oxygen. Okay? We'll look at this a little bit more so in a few slides. I'll make it more complicated for you. But no cytoplasm, no oxygen used. Okay? Think of this as molecule of glucose goes all the way through glycolysis, and we end up with a molecule of lactic acid and a couple of ATPs. Glycolysis is like a 13 or 14 step reaction. 13 or 14 steps takes longer to do than one. Okay, longer than one. So it's slower. You guys will see you may get 2 or 3 ATP out of this pathway as opposed to getting 1. It takes longer, but you get more energy. Okay. So there's some give and take in this. Finally, the last sort of set of things we're going to call oxidative pathways or an oxidative pathway. Oxidative means oxygen. This is sometimes referred to as aerobic. They're all used synonymously. Okay. So the pathways and the substrates for oxidative metabolism are located in the mitochondria. They will use oxygen at the end of the electron transport chain. So this is basically the Krebs cycle and the electron transport chain. Okay. This one's even slower because you got to go through all but the last step of glycolysis, or you have to go through a process called beta oxidation to break down fat and then move those molecules into the mitochondria and then run through another 14 or 15. Okay? Much, much, much slower. But you get a huge amount. Huge amount. Okay? So those are our sort of 3 groupings: immediate or phosphagens, non-oxidative, which is going to be glycolysis, and then oxidative, which I oftentimes will just refer to as aerobic metabolic pathways, which means the Krebs cycle and the electron Okay. Are we still doing okay? I'm going to put this here, and we're going to come back to it. So I want you guys to know what we're getting into. Okay. This graph attempts to show you the relative contribution of the immediate or phosphagen systems, glycolysis, and then oxidative or aerobic metabolism to the total amount of ATP needed to exercise for 5 minutes. Okay. So we have immediate stores here in the dark line. So basically, the first couple of contractions that you do for anything, you're pretty much using stored ATP and creatine phosphate right off the bat. But, okay. The other pathways are active, but they're a little lagging. So practically 100% comes from there. You will note that that is basically all gone within about 30 seconds. Okay, all gone, all used up. You will then note in that sort of 30 seconds, while the immediate is falling, right, what you will see is that glycolysis is ramping up. And after about 30 seconds or thereabouts, the vast majority of the energy for that exercise bout is coming strictly from glycolysis, from glucose into lactic acid. Then it begins to fall off, and anaerobic metabolism is going to begin to sort of increase and hopefully soon become the predominant energy pathway after a couple of minutes. Okay. You will note even out here, the immediates may all be gone, but you're still doing some of both of these. You're still doing plenty. Okay. Does that conceptually mean? It's the first thing that we're going to do to sort of conceptually. So if we said, Emma, stand up. Where did Emma get that energy from? You just stood up. Where did it come from? Good. Now she's standing here. Okay. You're standing. Just a couple of jumping jacks. Just don't hit Catherine or like bump yourself. We're doing some jumping jacks. Okay. We're blowing through our immediate. We're starting to ramp up glycolysis. Okay. At about 30 seconds, you can sit down. Thank you. At about 30 seconds, I'll show you guys. You've used all the stored ATP in your muscle in the first like 2 contractions. There's so little amount, it's gone. Just a couple of seconds. Most of you have 20 to 30 seconds worth of creatine phosphate in there, depending upon if it's very intense exercise. And it's all gone in about 30 seconds. Okay. Then you're going to get glycolysis, then we're going to get oxidative, kind of lagging a couple of minutes afterward. Anybody ever go for a jog and you feel good when you first start, and then from the first, then like that, like minute 1 to about minute 3 or 4, you're like, I don't feel so great. This feels worse than what it did when I started. It feels worse than the last time I ran at this particular like pace. And you go for a couple more minutes and you feel okay again. What you're experiencing is this intervening period, and we'll talk about why it feels uncomfortable a little bit later today. What you're experiencing is, I feel good until all my immediate stores are gone, and my aerobic pathways are not kicked in completely yet. So all I'm doing is making a bunch of lactic acid, and that makes your muscles feel unpleasant. You do all of it. You can push through that for a couple of minutes. It's not a problem. At very, very high intensities, you may not make it more than another 90 seconds or so, but you're right in there. And then as aerobic takes a couple of minutes to speed up, then it can meet your demands. Glycolysis, or at least going to lactic acid, falls off for the most part. And we're here and you're fine. Okay? Every time you do any kind of movement, this is what happens. This is what happens. When you walk, though, you stand up, you walk. You don't need here, you only need energy to here. So you can get a couple of minutes out of your immediate system. And that gives you plenty of time then, right, for aerobic to be able to kick in or supply enough. You're just barely moving, it's going to be down here. So all of this kind of gets shifted to the right. If you're doing super high intensity exercise, you may not make it to here. You may not be able to have enough ATP once phosphagen is gone and glycolysis is trying to do it all by itself. most of them. You guys understand that as a concept. Everything else we do today will make a little bit more sense. You guys understand that, I promise you, you will understand and know more about metabolism than half of our graduate students. Okay? Maybe not half, but still. Okay? This is all of them working all the time. Okay? And then within this, in the oxidative pathway, there's some carbs that are getting broken down, there's some fat that's getting broken down, kind of all laid on top of each other. Okay. Let's talk about those immediate oxygen pathways. As I said, you have a fraction of ATP that is stored in the muscle. That gets used up very quickly. The muscle or the body's preferential next metabolic pathway to make that ATP come back. Okay. So I guess I should write all of this out. We have a molecule of ATP. Some of you got this in the crossword cycles, some of you didn't. But what happens is I have a molecule of ATP, and I cut off a phosphate, right? ATP stands for adenosine triphosphate. So you have an adenosine molecule. Our organic chemistry teacher is rolling over in his grave right now, but I'm drawing ATP like this, right? But it looks like this, adenosine 3-phosphate. So call it. In the cross-bridge cycle, right, we hydrolyze it. So I now have adenosine diphosphate and a free phosphate, which we call an inorganic phosphate. Okay? What the metabolic pathway does now, this is the most important molecule that regulates everything in metabolism, and that's ADP. We need to find a way to turn ADP back into ATP. Okay? So what happens is there's a limited amount of adenosine floating around in your cells. A limited amount that floats around in your cells. All we're doing is just fluctuating the number of phosphates that are attached to that adenosine. Okay? Had ATP, I did something, I split it. Now I'm going to use a metabolic pathway, and I'm going to turn ADP back into ATP. I'm going to wait. Then if I need more, then split it again, I resynthesize again. And so you've got some number of ATP molecules that's set in a cell, and all metabolism is doing is just running this sort of circle. What we are doing, this is that transfer of energy. This is moving energy from a stored place in food and realizing it as we convert ADP back to ATP. Okay, so the creatine phosphate pathway. Oftentimes you'll see it abbreviated as the CP pathway. It's also, you will see creatine phosphate. If you ever read a paper, they actually call it PCR, which is weird, but you can see it done this particular way. You have a molecule of creatine that you get from eating meat. All my folks that want to take creatine as a supplement, eat 2 cans of tuna fish a day. It's cheaper and you get the same amount of creatine. Don't put me down for that. I don't like tuna fish. That's where it comes from. You eat stuff that has creatine in it. That creatine then gets digested and it goes and gets into your muscles. You then hook a phosphate onto creatine. So I made my ATP. I have a molecule of creatine phosphate sitting right here. And we're going to run with an enzyme and split the phosphate off and attach it to the ADP. And I have a free molecule of creatine, which at some point in the future, I will then put a phosphate back on. Okay. About 98% of all creatine is in the skeletal muscle. About 80% of you can consume extra creatine to get more into your muscle. About 80% of people are what we call a responder, and you can make it go up by about 20%. Okay. This is one of the useful things that if you're a sprinter or sort of a shortcut burn athlete, might actually be ergogenic. Be helpful. Have more readily available immediate energy. But this is the breakdown. I have creatine phosphate, it encounters a molecule of ADP, hydrogen, and I make ATP, and I'm left with creatine. And then at some point, once you stop exercising and you have plenty of ATP around again, this reaction goes in reverse, and I make the creatine phosphate. This is the fastest method of providing energy outside of just simply breaking down your stored ATP. This tends to be the first energy pathway used all the time. Okay? Problem is, the amount that we have in your muscle is limited. There's only so much space in a muscle for creatine phosphate. Most people have enough that it can support sort of all out heavy sprinting exercise for maybe 10 to 20 or maybe 30 if you're not quite at max kind of stuff. Okay. No. Yes.
So in health and fitness, you said that you were down on creatine and wasting money.
Yes. For the average person, yes, I do. Right? There's plenty of evidence that if you supplement with creatine because you have more energy, maybe you can do like one more rep when you're doing your weight workout or something. And there's lots of evidence that if you supplement with creatine, you get better hypertrophy than if you don't. And I say better, like 1 or 2%. But it's not because the creatine phosphate or the creatine itself is actually anabolic. It doesn't drive protein synthesis. You have more immediate energy, maybe you can work out just a little tiny fraction harder, and that drives a little more adaptation. It looks like she wants to say something. As does Michaela.
Really been considering, so like, yeah.
For a lot of people, if you take it, you will also swell up. You will retain water because when the creatine goes in, it's got a charge to it. It's going to draw water into the muscle fibers. And so you will look like you are have bigger muscles, right? It's just water. And so that stuff that if people that are in weight competitions and stuff, then have to take a salt pill and dehydrate themselves, extrude all of that. So there's evidence that it works. Yeah. It's just how many people really need that extra 2%. Right, versus what it actually costs. Some people may decide that that's a useful thing. Also, in my evaluation today, under the does he treat everyone equitably in those things? Someone suggested that my use of bro science was potentially sexist, and then I needed a similar term to also that was sort of sexist to men, that there were women. We needed a female equivalent of bro science. To which I say, okay, right? I often will say plenty of women are bros too. Bro is a gender neutral term, right? Bro is not gender. Bro is right. I got my shaker bottle and my wraps. Right, and I got my phone set out. I'm going to watch me squat, and I'm going to bench press on Monday. That's really the whole thing. To really be a bro, you have to bench press on Monday. That's just the way it is. Everything else we can wiggle on. So, but I was told. So, if anybody knows of something that would not be wildly offensive, that we could use that might include women into the bro science, please let me know. So. I'm guessing from Zach chuckling, Zach was not the one that said that on the course about it. So I appreciate we want to be inclusive of everything. But bro is not a gender term. So I'm sticking with that. Bro is gender neutral. So I don't know. So should we start calling it they science? I'm serious. I'm not being facetious. I don't know. Look, I want all of you to identify however you want to identify, and we will do whatever we can to make sure that we use your correct pronoun. I'm serious about all of it. I don't want anybody to feel like whatever I am doesn't fit, and so there's not a word for me. I'm very serious about that, right? The stuff on non-binary and all that kind of stuff and suicide rates is astronomical. We do not ever need to make light of this, ever. But I don't want to use a gender term if it offends people, But if you guys know something that we could call for the women that would not be, I don't know. Just let me know. Send me an email.
Riley, I was gonna use that.
Muscle moms. Okay. Is that now not inclusive of women that don't have kids? Or are you trying to be a mommy to your muscle? I'm trying to grow the muscle. I don't know, right? I'm just. Okay. Other Riley. For those of you that don't know, in health and fitness in the fall, I had Riley and another Riley, and they were a single entity. Right? I would just say, Riley, answer the question. So, pardon? Oh yeah, we had 2 Emmas and 2 Emilys last semester in health and fitness. Usually I will have like multiple, and you guys know what names. There's usually several Katies, Catherines, or something that are going to be in there. There's usually a couple of Madisons. We all know like whatever names. Like when I was in school, there were always 4 Chris's in class. It was Chris and Michael, and that was like half the boys in class. So those were just the popular names, Okay. Gotten that off my chest now. That was cathartic. If you have an idea, please let me know. Okay, so for all of our gender neutral bros, if you take the creatine, you will get, right? You may get there. Okay. All right. There is an enzyme that I want you guys to know, which you guys will see with all of our metabolic pathways. Again, it's just biochemistry. All of these reactions are generally driven by enzyme. Okay. I didn't make you memorize all of them. I still have nightmares from my own biochemistry class of having to memorize the molecular structure and the enzymes of every step in glycolysis and Krebs cycle, and I have nightmares about it to this day. So I had to learn all of the amino acids and their structures, and I don't remember which 2 I would always get confused, but it was not important. I'm like, there's a book, I can look it up. Right? When you're ever going to see a glycine, know that's different than lysine. It's okay. An enzyme called creatine kinase. The reaction that is driven, that's going to drive creatine phosphate, pull off the phosphate and stick it on to ADP, is driven by an enzyme called creatine kinase, CK. Okay? ACE generally means we're pulling a phosphate and we're sticking a phosphate. I'm sorry, a kinase. It's been a day. I did not sleep well last night. It's been a day. That's what's going on here. Okay? So the thing that regulates and makes creatine kinase work is the presence of ADP. Okay? You guys remember talking about redox reactions in freshman chemistry? How it does.
Well, I took Chem 2 last spring.
So you do a reaction, we've got creatine phosphate plus ADP, and we can note it like this, right? We're going to get ATP and creatine. This sort of thing in the middle denotes that it can go in both directions. And the reason it goes one direction or the other is that something increases on, if you increase the amount of creatine phosphate, it drives the equation that way. So we increase ADP from metabolic turnover, and it drives this reaction that direction. Almost every one of our metabolic pathways, almost all of our enzymes that drive them will upregulate their activity when they come into contact with ADP. If there's ever a question about what's the thing that makes metabolism go up, just say ADP. Okay? That's the general answer. You will also note that this reaction can go back the other direction. The same creatine kinase enzyme will pull a phosphate off of ATP and stick it back on the creatine and make the creatine phosphate back once you stop exercise. If you ever do a lot of heavy exercise and your muscles are sore and you go to the restroom and you pee and your pee looks kind of yellow, God forbid it looks like Coke or something. If it looks like Coke, go to the hospital, please. One of the things that is in your urine that makes it look that way is the creatine kinase. I need to get filled with the kidneys. You have a heart attack and you go to the hospital, they're going to take a blood sample and they're going to look for cardiac creatine kinase to see, you can tell if there's been damage to the cardiac muscle. In my lab, if we wanted to, we could take a blood sample, we could look for creatine kinase in your blood in response to muscle damage. When you're sore, we can look at it in those ways as a marker. It's a thing that's supposed to be in the cell, out of the cell. So if you ever go and you get a urinalysis, they'll talk about your urine creatine kinase. They might talk about your urine creatinine, which is sort of a derivative of the creatine. When I believe metabolism, I'm just trying to provide some lifelong context here. So when you go and get blood work done, you can understand things. Okay. So I want to spend just a moment talking about how we resynthesize creatine phosphate, because this has a really staggeringly important implication for athletes. Okay. Who lifted weights today or plans to lift weights today? Okay. Colin, what are you doing today?
I had back and buys.
Back and buys. How many sets did you do? 4. How long did you rest in between sets?
No.
Okay, we can't use Colin. Okay, we're gonna come back to that. Anybody rest longer than that? Anybody doing a real heavy strength day? Yeah, Kyle, how long did you rest? 2? 10.
2.
2. Buddy? Okay.
It's just.
Pardon?
I thought you were expressing
Right. Kirby?
the program I was doing, he was like, I'm doing
You're doing short rest period.
like, yeah, mine are not long.
Oh, are they? They're long rest? Hypertrophy training. Yeah, it could be. Okay. We can talk about that. Sorry, little happy days. So a lot of misinformation about if you do short rest periods, it increases the growth hormone release from bout of exercise, even though that increase in growth hormone doesn't actually get you any more muscle mass. And so people forever, if you were an SCA person, you just did hypertrophy training where you did like 45-second rest in between sets and you dropped the weight and it was moderate and all of these things. And it's a tremendous workout, but I don't think it actually helps hypertrophy much more than so. Okay, again, you guys are not helping me out here. It's okay. So let's just say you're gonna try to do 1 rep maxes today. Okay. If you look at the things, and I've yelled at many of you in health and fitness about this when we did our bench press 1 rep max, you need to rest longer. Well, when you stop exercising, jumping jacks, I'm using creatine kinase or make creatine phosphate into whatever you guys got, producing creatine. Brain is really foggy today. Doing this, I've depleted my creatine phosphate, boom, I stop. Okay? When I stop, energy demand bottoms out. I don't need to break this down anymore. Aerobic metabolism is still running. We've actually stimulated it by doing some stuff for about 30 seconds. So I'm going to, once you stop exercising, I'm going to start taking ATP made in the mitochondria and resynthesizing my creatine phosphate. If you look at what I used to think were the strength recommendations for resistance training programming, they would say you should rest 4 to 5 minutes in sets. That number was not pulled out of thin air. That number will get you to about 97% creatine phosphate resynthesis. This stuff has a half-life of, depending upon how well your mitochondria work, of maybe 30 seconds, 45 seconds. Like half of it is back, half. You kind of do your half-lives out, okay? Most of y'all can rest 2 minutes, you're getting pretty close, but if you really want to get this all the way back, you need like 5 minutes. It uses aerobic metabolism, okay? This is one of the reasons that when you stop exercising, you continue to have an elevated heart rate, you continue to have elevated breathing rate. Its metabolic rate stays elevated so you can make. Now, I'm going to mention a name and nobody throw things at me, okay? Lincoln Riley. Okay, the duck. It's become very commonplace now. But one of the things, right, in football now, Lincoln was known for is go fast, fast. Run a play, get right up back on the ball, run a play. Okay? It's football. Use creatine phosphate for 3 or 4 or 5 seconds, and you get to stop and walk and catch up, and you go again and you go again. 4 to 5 seconds. The football players don't have to be in that great of aerobic shape, right? You don't have to go very long. The better your aerobic metabolism works, faster you can resynthesize creatine phosphate. That's why it's important. Even anaerobic athletes, if it's intermittent, like soccer and basketball and football and these kinds of things, it's really helpful because when you're resting between plays or when you're resting while somebody's got the ball out of bounds or something, you can resynthesize more creatine. So this whole idea of resynthesis is termed the creatine phosphate shuttle. Okay, we use ATP made in the mitochondria. There's a creatine kinase enzyme located at the edge of the mitochondria, and it basically shuttles the phosphate out from in the mitochondria, made in aerobic metabolism out and hooks it on creatine. Okay. If I lost anybody with my detours and my foggy brains yet. Kayla? Yeah.
But like just
You don't have to eat fish. Pretty much everybody has. I mean, there's probably some people that have very little, but most people, if you eat any kind of fish, chicken, or anything that has amino acids in it, you're gonna. There seems to be a higher concentration in fish than there is in.
like we all.
I don't know the answer to that. I know lots of people that are vegetarians that are still able to sprint and do things, so they're getting some creatine from somewhere, but I'm not sure. It's a good question. I don't know. My master's students, Lagoon. Okay. I want to do one more thing before we jump into a different reaction. Okay. I want to do an example. Who has a little foggy brain like me today? Stayed up too late. Avery?
I didn't stay on.
It's okay. Would you mind being a guinea pig? Just come stand up, stand right here, sort of behind Julia and Hannah, right in front of Kiara, right back here. I'm going to give you guys one more, what I think of as sort of mind-blowing thing about metabolism that I want you to keep in mind. Okay? All of the things that we've talked about, all of these reactions take place by random chains. Okay? By random chains. Let's say Avery is a molecule of ADP. Okay? You're going out for Halloween next year. Okay? This room is a muscle fiber. Okay? Now, close your eyes and just start walking around.
That's dangerous.
Right? You're going to bump into things, right? You're going to bump into things. Got a lot of desks, just going to bump into a lot of desks. Okay? If our ADP molecule is just floating around inside the cell, it's going to float around until, let's say, Michaela is a molecule of creatine phosphate and Ty is a creatine kinase enzyme. She has to float around until she bumps into Michaela while they're also very close to Ty, so that then we can turn her from an ADP molecule into an ATP molecule, right? And then Michaela now doesn't lost her phosphate. she's creatine and she's just going to float around until we stop exercising. And she bumps into a creatine kinase 600. So if we wanted Avery as an ADP molecule to have a greater chance of bumping into creatine phosphate, what should we do? Should we have just Michaela as creatine phosphate in the room? Or should we have like half of the rest of you be creatine phosphate? If I put more creatine phosphate in the room, the chances that Avery blindfolded runs into one of y'all goes up. If I put more creatine kinase, it's not just Ty, it's more of y'all, right? Or if I put more mitochondria in here, there's a greater chance that Avery as an ADP molecule will bump into one of them. Okay? This is how metabolism works. Okay? It's not just ADP and ATP. She could be an ATP molecule, and she's got to wander around blindly until she bumps into a myosin ATPase to break a cross bridge. Okay? All of the things that we show happen by random chance. And it blows my mind that anything ever happens. Right? This is how physiology works. It's crazy to me. But this will make you guys understand. When I start dumping more glucose in, we take not just one Avery, there's 20 Averys, there's 20 glucose molecules in here. So there's a much greater chance that one of them will bump into whichever of y'all is the, is a, God, I can't think of the enzyme. It's not phosphorylase. Oh, God. It's okay. There's an enzyme that puts a phosphate into the kinase, but it puts a phosphate onto the glucose molecule and keeps it in. But it's the same thing. As more molecules of a thing, either an enzyme or a substrate or ATP or ADP float around in the cell, the chances of it bumping into the thing that we want to happen stop. Okay, thank you. Right. It is a kinase. No, it's a particular kinase. It's hexokinase. Yes, thank you, Kelly. Boom. Okay. I'm gonna take a break in a minute. I'm gonna go get some caffeine. I should have had it an hour ago. Okay. Many of y'all feel like serious. Okay. So that's how metabolic reactions take place. Okay. These things are just floating around. So when I say that as ADP levels go up, it drives all of our reactions. The reason that it does is there's more of them. There's more Averys wandering around in the cell to bump into the things that we need to make more ATP. Okay? And there's more glucose in a cell. So there's more free fatty acid in a cell. There's a greater chance it will bump into whatever it is. And I take those of y'all that have a lot of type 1 fibers or a lot of 2As, and you run or bike or row a bunch and you have a shit ton of mitochondria in your cell. There's a much better chance that whatever our molecules are going to bump into the mitochondria. It's going to be good. Okay? It's all this idea, I mean, it's just diffusion. Just kind of the law, I don't know if it's the law of mass action or whatever it is, but it's just diffusion. Okay? So if you double the substrate, you double the speed of the reaction. You double the number of enzymes, you double the speed of the reaction. That's some wild biochemistry that probably makes Riley want to throw things. Y'all do Michaelis-Menten plots in biochemistry, Riley? Okay. She knows. Okay. Let's do myokinase. We'll do this, and then we'll do myokinase, and then we'll take a break. You don't have to know this, guys. This is just how we would experimentally measure, and we know what happens with creatine phosphate in the muscles. Okay? This is the reaction, the mitochondria, cytosol, the myofibrils. This just shows all of this as we're sort of shuttling stuff from creatine phosphate to the myofibrils, and then when we stop exercising, we resynthesize from the mitochondria. What you all see here is the amount of creatine phosphate in a muscle measured in an MRI unit. We do a thing called magnetic resonance spectroscopy. Okay. And they take the person, it's usually in their calf, you go plant flex, boom, 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 boom. Run metabolism, deplete the creatine phosphate, and you stop. And we watch over time as it sort of slopes its way up and resynthesizes itself. If I want to know who in here has the best functioning mitochondria, put you all on the magnet and I see who has the fastest rise and steepest slope of increase of this resynthesis of creatine phosphate. It's not who has the best VO2 max. It's not some of those things. It's this. This is how we know a lot about this stuff. Okay. The lab that I worked in, also sort of adjacent to when I was a PhD student, they did some of this stuff. Okay. They did some of this stuff. The guy that I did my master's degree with was one of the people that figured out how to do this when he was a postdoc. Some kind of really cool, interesting stuff. Okay. Really quickly, we'll do myokinase and then we'll talk about glycolysis. Myokinase is just like creatine phosphate. Okay. Except rather than bumping into a creatine phosphate, occasionally two ADP molecules will bump into each other. Okay. And they will be in the proximity of the myokinase enzyme. And two ADP get turned into one ATP and one AMP. So two diphosphates go to one triphosphate and one monophosphate. Okay. This happens a lot, but it's a little bit less frequent. You don't have a lot of myokinase enzyme. It's not that great for us during exercise to take our ADPs and do this too, but it does happen. So. But it's the same idea. We got to have two Averys, and they got to bump into a myokinase. Okay. Again, you don't have to know numbers. I just want to show you guys something that may illustrate and be relative on how much sort of total phosphagen, kind of immediately available energy we have. How much of that comes from myokinase, how much comes from ATP, and how much comes from creatine phosphate. Okay. So you've got about 11. Okay. This is about 11 kcals of energy from the immediate phosphagen system per, right? That's per sort of total muscle. Okay. The vast majority of that comes from creatine phosphate, right? We have about 4 times, almost 5 times as much creatine phosphate in a muscle as we do ATP. It's just going to be funny. There's just a little fraction. Okay. If I did this for glycolysis and I did this for the aerobic pathways, it wouldn't be 11 for the aerobic, it would be like 5,000. This giant, huge number. Problem is, it takes me a little while to get all of those things made. And so, right, evolutionarily, when the saber-toothed tiger comes running at you, you got to move. You got to move right now. At time to be like, pause. Like, electron transport chain needs about 2 minutes to kind of get spun up. Okay, can you hang on? You got to run. So that's where this is going to come from. Okay, let's pause here. Take a little break. I'm going to go get back in. Here you go. Pardon?
At graduation, yeah, they explained down the stairs when you're walking. So I was like, oh, no. Like, live down like five feet. This picture and there's just. Yeah.
Oh my God. Yeah.
It seems bad.
Surprise me if we convert other readers into it or something. Not enough. Wow. About the supplement.
And like you write, I mean,
I'm gonna die or something.
Yeah.
Okay.
We lost some people. They just got up and pieced out. Matt?
Compare like, today would be more beneficial or like drawn out. That cycle like, drawn out. Like it or.
Okay, Michaela's already stressed by it.
You just had it as.
We did, I know, we just had.
Yeah.
Yeah. Huh?
Yesterday we had to draw a couple things, they would let us know what we need to be able to draw things. Like the cycle thing.
I mean, I feel like that's just, I mean, I guess that was a problem. And I saw some answers. There was some interesting looking, unless you're young.
I did.
Several of y'all drew beautiful motor neurons in their axons, but no junction. all labeled, everything perfect, beautiful. No more, but it was not the neuromuscular junction. And so you very clearly just didn't understand what I was asking. So that makes sense. Gone. Okay, one conversation, one conversation. I generally operate under the assumption that if there's like a structure or a thing, that you will know it and you will be able to draw it without me telling you. However, because I feel like if I say you got to be able to draw this, I'm not to tell you like be able to draw like 10 things. So it's not the world's like most like beautiful like giveaway. Like this is the thing, right? Like, this is the question. But I can take that under advisement if you all think that would be like if that's going to hinder or help how you study, then like we can talk about that. I guess I can think about it.
So just be prepared to draw.
Yeah, like a good pathway. This is going to signal to this or something like that. Yeah. Okay. Let's talk about glycolysis. Okay. All the time, all the while we're breaking down creatine phosphate, we're doing the myokinase reaction. We are also running glycolysis. Always on. Okay, it's always on. So, what glycolysis is a series of reactions where we oxidize or break down glucose and turn it into lactic acid. Okay? And that process is complicated. We found lecture 8, biology of redox reaction. Somebody needs to like chat GPT, whatever this is, right? And just teach via chat GPT. I'm not going to record lectures for y'all next week. I'm just going to ask those questions to chat GPT and just kick out stuff and I'll make Siri read it or something. We're making ATP from ADP. Okay? Very, very simple. Except that it's not. Okay? But I'm going to simplify this for you all. Okay? This sarcolemma. Let's just say I have the glucose molecule here. Okay, so we're going to extend our sarcolemma, make it come down here. This is a nice fiber, right? And this area in here, this is the cytosol. I have a glucose molecule. Okay, that glucose molecule is going to get broken down in glycolysis through a series of steps into something called pyruvate. Okay. How many carbons does glucose have? Anybody remember? 6. Okay. Pyruvate does not have 6. Anybody know how many carbons pyruvate has? It's got 3. And
Is it really? Yes.
that's 3. So you're going to break glucose down and make 2. We must conserve our carbons for now. You're going to make 2 molecules of pyruvate. Okay? I want you to know this. Glucose to pyruvate. That pyruvate, right now we're going to talk about converting that pyruvate into lactic acid. There is another possible fate of said pyruvate that we're not going to talk about yet. Okay? So it's going to do this. Glucose to pyruvate, pyruvate to lactic acid. That's the steps that I want you to do. Okay. Yes. The number of carbons is 100% key and important. is we're not going to do anything in glycolysis, but as we go into the aerobic pathways, we're going to start losing carbons. And that's where the carbon dioxide you breathe out is come from. So, we're going to take glucose. Now, it's important to make a distinction about where the glucose comes from. Okay? This glucose molecule can come from one of two places. It can come from out here in the blood, okay, which is sometimes termed a free glucose molecule, or it can come from, you have this matrix of stuff over here, that's glycogen, and I can get a glucose out of the glycogen that's already in the cell. Okay? The reason that this matters is our energy yield is going to be the amount of ATP we get is going to differ by 1 ATP depending upon whether the glucose comes from blood or whether it comes from glycogen. So this entire reaction, and I'll get you guys a little bit more, just a couple of enzymes and a couple of other details in a second. Glucose to lactic acid. If the glucose comes from the blood, you make 2 ATP. 2. If the glucose has come from glycogen in that muscle that was broken down, you make 3. Okay. So we're getting 2 or 3 times the amount of ATP from glycolysis that we do from our phosphagen. Okay. The downside of this getting more energy is it's slower, so it takes longer to run. Okay. However, it is faster, and in some instances has to precede the aerobic or the oxidative pathways. And there's one other problem with all of this. This is probably the primary limitation. Okay. Lactic acid, again, more chemistry. You put an acid in water, it does something called dissociation. Okay, dissociation. So what that means is the cytosol is mostly water. When you make the lactic acid, it dissociates into lactate and hydrogens. Okay, hydrogens. Lactate is our friend. It's a 2-carbon molecule. We're okay. We can do things with lactate. We will do things with lactate. Problem is the hydrogen ions. Okay. As we see when we get to fatigue and various things, the hydrogen ions inhibit everything. Inhibit glycolysis. Inhibit the cross-bridge site. They inhibit the electron transport. Okay. In addition to all of that, they make your legs hurt. That burning sensation, you often feel that sharp burning sensation during exercise. That's from the hydrogen ions from. Okay, so we've got all of this. Okay. So this is the rest of the pathway. Okay. Going from glucose to pyruvate. This is called the Embden-Meyerhof pathway. Okay. Assume we haven't discovered a step. This is from my biochemistry book that I used in the spring of 2000. And we should all be happy I didn't burn at the end of it. But it's glucose, okay? And then you make glucose 6-phosphate, and then it goes to fructose 6-phosphate, and fructose 1,6-phosphate, right? And then you're going to get these 2 molecules, this dihydroacetone phosphate, blah, 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 phosphoglycerate, right? Do all the way down here, and you get pyruvate. All I want you guys to know, glucose goes in, pyruvate comes out, okay? I'm going to point out, though, a couple of steps here that are important because it helps us understand our energy. Okay? There is an enzyme called hexokinase. If I have a molecule of glucose that comes out of the blood, right? Comes out of the blood. Hexokinase is going to stick a phosphate on it and trap it in the cell. so it doesn't get away from us. Okay? Glucose comes in, hexokinase tags on phosphate. That has cost us energy. Okay, that's cost us energy. That's the input of 1 ATP. That's how we get glucose 6-phosphate. We're going to move on down, bing, 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 bing. We're going to get to another step run by an enzyme called phosphofructose. Okay, which is going to stick a phosphate onto our fructose. Turn the glucose into fructose, right? They're going to freak people out and like, I don't want to eat high fructose corn syrup. Guess what? And all the other sugar you do when it goes through glycolysis, it all gets turned into fructose. Okay. Phosphofructokinase, also sometimes called PFK. I mentioned PFK, and I want you to know PFK because this is what we call the rate limiting step of the reaction. To be rate limiting, it means this is the slowest step in this entire pathway. Okay. This is the thing Avery has to wait the longest to bump into the entire pathway. Okay. So I want you to know hexokinase, that puts 1 phosphate on. PFK puts a 2nd phosphate on. So if it's come from the blood, I've now inputted 2 phosphate, that's cost me 2 ATP. If it came from muscle glycogen, it comes out of muscle glycogen as glucose 6-phosphate. So it can skip the hexokinase step. Okay? So it actually comes from, going to come in below the step. So I don't have to waste an ATP. We're then going to work our way down. We're going to pull off some electrons and hook them onto something called NAD, which is an electron carrier. Okay. And then at various points as we come down, we're going to make some ATP here and here. And because we've got 2 molecules going through, we make 2 here and 2 here. Okay. So in doing that, we've put 2 in, we get 4 out. That's why we get 2. Okay. If we skip the hexokinase step, we put 1 in and we get 4 out, so we make 3. Are you guys with me? Glucose to pyruvate, no hexokinase, no PFK. Okay. We're going to do one more enzyme that controls this step, pyruvate over here, lactic acid. Okay. One more enzyme. Okay. So I just basically did this. So at the end, do I not have a picture? Of course I do. Okay. My apologies, this is a little bit out of reach, but what we're doing here is there is an enzyme. We're going to go from pyruvate or pyruvic acid to lactic acid. There's an enzyme that's abbreviated here called LDH. So LDH sits right here. LDH stands for lactate dehydrogenase. Lactate dehydrogenase. When LDH comes in contact with pyruvate, it makes lactic acid. Okay? That's the big thing. The other thing that we're going to do when we go to lactic acid is we're actually going to take the electrons that we had, okay, that we had already stuck onto NAD, and we're going to take them back. LDH grabs those electrons back and converts pyruvate to lactic acid. So don't worry about all of the sort of steps that are going to be right now. Let me back up just a little, okay? Just wanted to show you kind of what's happening. Avery.
But our ratings like
So this?
Yeah.
This is glycolysis.
Oh.
This is glycolysis. Okay? We're not using oxygen anywhere. right? We're making pyruvate, and that pyruvate in this instance is going to lactic acid. There's 3 enzymes I want you to know: hexokinase, phosphofructokinase, lactate dehydrogenase. That's what I want you to know.
Now,
this kind of summarizes, we're going to get 2 pyruvates through the end of Meyerhoff pathway. If it's coming from the blood, we're going to make 4 ATP and have used 2, so we make 2. Here's the thing. I've shown you guys this step.
we're going to call, some people call this anaerobic glycolysis, and I want to like throw things out. All glycolysis is anaerobic,
right? But this is going to be pyruvate to lactate, pyruvic acid to lactic acid. Okay,
which is what I've shown.
the other possible fate of pyruvate is that rather than going to lactic acid, it can go into the Krebs cycle. Okay, so they can go in the Krebs cycle. We'll talk about that in a second. Make some ATP. And we may or may not be sort of converting NAD into NAD.
These electrons will become important if we can get them into the electron transport chain.
That's where we are.
Clear as mud. I know we've done a bunch today. Okay. Maybe when I put this here that I wasn't going to want to do this, but we'll talk about it. Okay. There's a metabolic rate. Metabolic rate that we term the lactate threshold. Okay. Lactate threshold. If I did a finger stick on every one of you in here right now, okay, got a little drop of blood from your finger, I can look in that blood and I can find lactate. Because why? Why would there be lactate in your finger stick? It was our first like axiomal rule of metabolism. You're always making some lactic acid. Always. Okay. It's a small amount because you're at rest, but there will be some. If you start walking, even though you will probably be making more lactic acid to get more energy as you start walking, when we do a finger stick, that level is not going to go up. Okay. You start jogging, it's probably still not going to go up. You start jogging fast, it may then begin. So there is a metabolic rate, a rate of energy production we call lactate threshold. And that is defined by what is the energy use rate where lactate begins to increase in the blood above resting levels. Okay? Above resting. And it looks something like this if we graph it. Here's a person on the bike. They're cycling up to, I don't know, about 220 watts. They're pretty fit. And here's at rest. And this is their blood lactate level. Very, very low. And they get to a place where, okay, now it's going to start to increase. Okay. What lactate threshold tells us is a place where glycolysis is starting to run more and more and more. It may not be quite predominant yet, but we're getting close to glycolysis being our predominant. When you run or bike or anything over lactate threshold, you'll notice this is the rate at which when your muscles are going to really start. This is going to be a predictor of fatigue, a predictor of task failure, et cetera, et cetera. Okay. Okay. The other thing to keep in mind,
make lactic acid. This is going to be kind of a crazy thing. But I'm going to take some of that lactate. And I'm going to put it into the Krebs cycle. Okay. That is called the lactate shuttle. When the lactate gets traded around between muscle fibers, or it stays in its own muscle fiber, and it gets put into the mitochondria, and it gets used as fuel. Right? All of you make some lactic acid all the time. If you make quite a bit, you stop exercising, it's going to clear itself out and go away, mostly by the lactate portion, the carbon portion goes into the Krebs cycle and gets turned.
We're very clearly going to have to cut some of this stuff down, or we're not going to be able to get through all of it in a couple of days. So, okay. Aerobic metabolism. Talk about what happens here. Okay. Where's the Krebs cycle? This is this thing that it's in. Aerobic metabolism, we're going to break down glucose or fat or proteins into CO2, water, couple that with the synthesis of ATP. All of this takes place in mitochondria. So this glucose that we were talking about here, that glucose has been made into pyruvate. That pyruvate goes into the mitochondria and it goes into the Krebs cycle. Later on, you guys will see when we do beta oxidation, I can have a molecule of fat that comes in from over here and fat goes into the Krebs cycle. Okay. This is the primary ATP pathway. You guys are resting right now. This is the primary way that you're getting ATP. Okay. It requires a constant supply of oxygen. We'll see that at the end of the electron transport chain. We need a lot of oxygen. It primarily uses pyruvate or glucose and fat. If we supply it glucose and fat or a substrate and we keep it having oxygen, its capacity to make energy is not exactly limitless, but it's very, very, very high. Problem is that its maximal rate is quite a bit slower than creatine phosphate, quite a bit slower than glycolysis, and is limited by oxygen. Right? So because of all of that, it's going to take a little bit longer. We're going to make a huge amount of energy. Okay? This occurs primarily, and I need to change how this, I don't know what actile is, but it occurs in the mitochondria in three phases. We're going to convert the pyruvate into something called acetyl coenzyme A. The coenzyme A, the acetyl group is going to go through the Krebs cycle, and then we're going to go through the electron transport. Okay. And here is the Krebs cycle that you guys have all seen. Here's pyruvate. So what I want you guys to know about the Krebs cycle, pyruvate goes in. Pyruvate gets converted to acetyl coenzyme A. You remember anything about your organic chemistry or biochemistry that you didn't take? Pyruvate has 3 carbons, acetyl-CoA has 2 carbons. We lose a carbon here as carbon dioxide. This is where the carbon dioxide that you breathe out is going to start to come from. We then stick the acetyl group into the Krebs cycle onto something called oxaloacetate, which has 4 carbons, and make something called citrate, which has 6 carbons. I don't care that you guys know this. Pyruvate gets converted to acetyl-CoA, the acetyl goes in, and we spin ourselves all the way around the Krebs cycle. Okay? That's what I want you to know.
As it goes around, we're going to go from 2 carbons to 6 carbons. And then as this moves, we're going to pull carbons off here, CO2, CO2, okay? Now we're down here to a 4 carbon. And then as we spin and we basically change the biochemical structure of these molecules, we're going to strip electrons off and bind them onto NAD and FAD to carry electrons. So for every pyruvate that goes through, we make 3 NADH molecules and 1 FADH molecule. And we also make 1 molecule of ATP. So pyruvate goes in, make it into acetyl-CoA. Acetyl goes into the Krebs, spin around Krebs. You make CO2, 1 molecule of ATP, they reduce these electron carriers. That's all I want you to know. You don't have to memorize all the steps, you don't have to memorize all of it. Okay.
Lots of size out there. How are we doing, everybody?
Okay, this maybe this right here. So where is ATP made in glycolysis? Like in which step? Are we using?
It's like right here.
Okay. And it's either 2 or 3. Okay.
Good question. Okay. This just sort of sums all of this up. I want to point out one enzyme we are not responsible for. When we did the muscle biopsy stuff back last week, we talked about one of the things that you can measure. You look at mitochondria and their capacity in a muscle biopsy, and you measure something called FDH, which stands for succinate dehydrogenase. Sure, one of those. Okay. You don't have to know it. I'm not going to ask you what step it's at. I just wanted to point it out because we had mentioned it before. Okay. Okay. Now, after we've done all of this, we're going to take all of those electrons that we bound up in the Krebs cycle, and maybe the electrons that we bound up here as we went from glucose to pyruvate. We're going to take all of those electrons to the electron transport chain, and we're going to use those electrons to create a concentration gradient and drive an enzyme that turns ADP. Okay. The electron transport chain is going to be located on the inner membrane of the mitochondria, and it contains things called cytochromes. Cytochromes have iron in them, so they're very highly positively charged. Okay. NADH, FADH enter the chain at different places, but they then give up and donate their electrons. Okay. And then the 3 molecules of NAD and FAD go back over to the Krebs cycle to pick up some electrons. We then transfer the electrons from one cytochrome to the next. It goes ping, 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 ping down the chain. That helps us to pump hydrogen out of the mitochondria and make a concentration gradient. And then we let those hydrogen flow back into the mitochondria, and that drives this ATP synthase. Gets us ATP. Okay, that gets us ATP. Now, I'm going to show this down here, and every book you read comes up with a different answer now. So the most recent book that Dr. Mike gave me for this, it says that we make 2.5 ATP molecules for every NADH molecule that enters the electron transport chain. You can't make half an ATP. So half the time it makes 2, the other half of the time it makes 2. With FAD, it's 1.5. So you make 1 or you make 2. So we take all of these electrons that we've pulled off of our substrates in the Krebs cycle, and we use them to move down the electron transport chain and drive the synthesis of ATP. Here's the change. Let me just show you this. I do not envision a scenario where I ask you to draw this. Okay? Make that very clear. But here's the outer membrane of the mitochondria. Here's the inner membrane of the mitochondria. Okay? You've got here, the very inside is called the matrix. This is where the Krebs cycle is, and it's down in here. Here comes NADH, and it donates at cytochrome 1. FADH donates at cytochrome 2. And then those electrons are going to get moved and pass from 1 to 2 to 3 to 4. All of that movement of electrons gets coupled with moving hydrogen out of the inside into this outer membrane space here. This funky looking thing looks like it should be in Star Wars. Right here, this is the ATP synthase enzyme. What happens at ATP synthase is we let the hydrogen come back in. Then that drives ATP synthase to put a free inorganic phosphate into ADP. So as you guys are sitting here right now, this is happening over and over and over and over again. Help us make a huge amount of it. Okay? That's aerobic metabolism. Hi.
1, 2, 3, 4, that's the cytochrome.
Yes, the 1, 2, 3, 4, those are in fact the cytochromes. Taylor?
So, on two sides of this, it says on
I should say into the outer compartment. It's actually, so we pump it out from inner compartment to outer compartment, and then we let it diffuse back down its concentration gradient. It's not actually a pump in here. This is just passing down its gradient. And that actually creates energy, which lets us do this in a way that I don't understand because I'm not a biochemist. Okay. This is the same thing, guys. It's just trying to show you, this is the matrix inside of the mitochondria. The electron transport chain, this is the inner mitochondrial membrane, should actually be in here. It's just trying to show you guys how it's actually not the most accurate, to be 100% honest. There should be another membrane here where these things are. But this just shows, here's the Krebs cycle. Here you've got pyruvate coming in from glucose. There's the acetyl-CoA. Round and round the Krebs cycle we go. We make NAD and FADH. They donate, we make ATP. That ATP then gets dumped out of the mitochondria into the cell. Okay. We'll see later. We also have free fatty acids that are going to be in the muscle that get pumped in. They're going to then go through a process where they're going to come and get broken down so they can go into the Krebs cycle. So all of this is happening simultaneously. I like that the slide shows, picture shows all of it. That's kind of what okay. Okay. So I like this picture because it's kind of what I drew you guys. Carbohydrate, this one's coming from glycogen. So we're going to do glycolysis and make 3 ATP. There's going to be some hydrogens or some electrons that we're going to move from that breakdown. We make pyruvate. Pyruvate gets shuttled over into the mitochondria, acetyl-CoA through the Krebs, making CO2. Where it says hydrogens, what happens is when we pull the electrons off, the hydrogens follow. So we pull the electrons off, we make some ATP. In doing all of this, right, we're going to make ATP and we're going to reduce our NAD. So when you put all of these things through, we're going to end up with our count, our ATP count. Okay. You're not responsible for the ATP count. Not going to make you responsible for trying to do that math and figure everything out. Okay.
Plus, they just keep changing the math on us no matter what, right? Like next week, they'll be like, no, you get 2.2 ATP per NADH. Okay. This again is just like a 14th way to try to show all of the same things, all the pathways together. Okay, glycolysis in the cytosol, we go into the mitochondria. There's the Krebs cycle. There's oxidative phosphorylation of the electron transport chain. ATP comes back out. Fatty acids are coming in, they do beta oxidation, and they're both going to go in with acetyl-CoA. Okay. So while you guys sit there right now, all of the free fatty acids that you had at lunch, if you're like me and you forgot to eat lunch because your tummy was not feeling great, then I've released the free fatty acids from adipose tissue, or you ate some sugar that's going through glycolysis. This stuff is going to get fed into here, and it's going to go there. Okay. Holly, you okay?
Oh, yeah.
Okay. What'd you have for lunch?
This
Too much of this now, right? Not enough of this. This is my preferred way. Where are the carbs? Give me some Starburst or some Skittles. Okay. Okay. The last like 10 minutes, we're going to take a step back and look at all three of the things that we've talked about today together. Okay. Nora will start doing rate control and all of this. Okay. So I'm thinking about how to show this, and I'm not 100% sure. And so, Alan and Bailey, I'm sorry. I'll try to draw this way over here where you guys can see. Okay. So we're going to draw a graph. This is how much ATP we need to do something. Okay. This is how much you guys need to sit there. Okay. This is how much you need to walk. That's how much you need to jog. Okay, Captain? Okay. You almost knocked your cup over, didn't you? Okay. This is how much I need to sprint. Okay? You guys can see the amount of ATP that we need. Okay? Now, at rest, while you're just here not doing much, okay? Let's make the assumption at rest, okay, that aerobic metabolism, your ability to make ATP, breaking down carbohydrate, free fatty acids, at rest gives you this amount, okay? While you're resting, that pathway is running as slow as it's ever going to go. It gives you this amount of ATP, okay? So while you're sitting, I make plenty of energy from aerobic metabolism to provide all of that energy, okay? Therefore, I rarely have to use creatine phosphate or glycolysis to do anything, okay? When you start walking, right when you first get up, there's going to be this amount of energy that I have to provide on top of what my resting aerobic pathway is providing in order to be able to walk. Okay. So where is this energy coming from? Okay, good. Creatine phosphate, anyplace else? Good. Okay. So when I go from sitting to walking, this is what's happening. But you will note I'm still getting, when I'm walking, a majority of my energy for walking is coming from aerobic metabolism.
Now, tomorrow it's gonna probably blow y'all's mind when I tell you, once you've been walking for 5 or 6 minutes, the amount you can get from aerobic metabolism goes from here, like up to there. Okay? But basically, that's my extra that I get. When I take off and I jog, right, then that amount of extra that I need gets bigger. So I have to use more creatine phosphate and more glycolysis. And when I go to sprint now, there's this giant amount that I'm going to need extra, which is why when I'm sprinting, especially early on, creatine phosphate and then maybe glycolysis are going to be the predominant energy pathway. Okay? Does that make sense? As much as anything that we've done today, this is really important to me that you guys understand. You can memorize the pathway, you can memorize how much ATP you get out of the whole thing, but this is what's happening. Okay? You're sitting and metabolism is running and you're getting plenty from your mitochondria, so we're good. You start walking, we need a little bit of extra, so we get it from here. You start jogging, we're about 50-50, right? We're going to get it from here until aerobic begins to kick up. And then you sprint, and I can't do this. So then, as creatine phosphate gets used up, after 20 seconds of sprinting, even though my energy demand is identical, I actually can't fill all of that space. I can only fill it up to here, let's just say. So what happens? I slow down. I do not make enough energy to be able to continue sprinting that particular pace. Okay? Every time you go and exercise, this is what's happening. There's this balance of I need a certain amount of ATP to do this task. Where am I going to get that energy from? It's available from multiple places. Ideally, we want to bring it from aerobic metabolism. We'll see tomorrow because we don't make any harmful byproducts from aerobic metabolism. We're not going to run out because we got a bunch. We don't make hydrogen ions, so that's the best place. But sometimes that's not enough. So we got to bring some from someplace else. Okay? And these someplace else may run out or may make hydrogen, which is going to be bad for us. And so therefore we can't keep walking at that pace. We got to slow down. We can't jog or run or sprint. We got to slow down. Okay? Last thing. We're all going to go take a nap. Okay? Right here. While you guys are sitting here right now, the vast majority of your pyruvate that you've made goes to the credit. Okay? Vast majority goes over. Small amount comes here. Why, as you exercise at a higher intensity, is more of the pyruvate and start from this direction. The balance between where the pyruvate is also really important for determining how much energy from aerobic metabolism of carbohydrate versus how much anaerobic energy. What do you guys think determines this? Kayla? Okay, oxygen availability. Sure. If you don't have any oxygen, that's going to trip some of that. Okay. Most of the time, though, we have a lot of oxygen. Remember our example of Avery wandering around in the room blindfold.
What was your question?
Why would, when we start exercising at higher and higher intensity, why would more pyruvate start going into lactic acid rather than it going?
Because lactic acid and lactic, and you're not using oxygen, it gives you energy quicker than it takes for oxygen, for lactic acid to go through the entire Krebs cycle and like any time to catch up to that aerobic high usage.
That's basically correct. Right, that's basically correct. As exercise intensity goes up, you guys will see. We start dumping huge amounts of glucose from the blood into the muscle. We start breaking down glycogen in the muscle. So the glucose supply here is way up. When there's more glucose, more of the stuff downstream is going to happen. That's our example. So more glucose means I have more pyruvate. At some point, okay, at some point, I'm going to run out of a capacity to stick that pyruvate into the Krebs cycle. Krebs cycle is slow, it's backed up, or something is going on. When that happens, then the natural thing is going to be, well, it's not going that way. Let's go to lactic acid so we can keep glycolysis running, keep breaking down glucose. So, this is going to be the key thing. Beta and pyruvate is one of the things that we're very interested. So if I get more Krebs cycle, I can take more pyruvate. I have less Krebs cycle. Less mitochondria. Less can go there. So it starts to ramp up. That's going to be one of our things we're going to talk about. We're talking about the speed of these reactions and how that kind of controls what I'm working. Okay. Do not feel like I did a particularly awesome job with this. We'll regroup tomorrow. Okay? We'll regroup tomorrow. If you have specific questions right now, you're like, you totally lost me, let me know. But I think
And then like, yeah.
Sure, we can figure something out. Tell me on Thursday. You'll be here. Yes. Remind me on Thursday.
Very positive out yesterday.
Yeah.
Since I took the class activity on Friday. How to make that.
Good. Two options. One, it will neither count for you nor against you. You just get another.
Okay.
You'll have one fewer assignment. than everybody else. Or I can let you. You can then you can. Either way, doesn't matter to me. We don't even have to make that decision today.
Okay. Okay, what was it?
It was about like I made them like pick out like how strong could you get and when and how and all of that. So